All right. Okay, so there kind of what I wanted to cover, and we have more to cover, but main things just to keep track of what we're doing right now is just what are polar coordinates? How do you label points, or how do you plot points with polar coordinates, and then how do you come up with multiple representations of the same point in polar coordinates? The next things that we're going to do are we're going to convert between polar and Cartesian, and so the big concepts that you want to be comfortable with going into multivariable calculus, so Calc 3, is convert to and from polar. So we want to be able to do polar coordinates to Cartesian, we'll say polar points. So the polar coordinates of points to Cartesian points. And then we want to be able to convert polar equations of graphs to Cartesian and backward. And so I think we'll probably get to the first set of that today. So converting between points, and then tomorrow we'll talk about converting equations. There is calculus behind all this. Unfortunately, we don't have time this semester to go into that. But if you take Calc 3, you'll go into some more with all of this stuff. Okay, so one thing to note is that when you look at something like this, so like if I give you the point, let's say 2 comma pi, most of us would probably assume that that's polar, but there's nothing about that point that actually indicates that it's polar other than if it's clear from the context. So when you write that, this could mean r is 2 and the angle theta is pi, but it could also mean x is 2 and y is just about 3.14. So like to the right 2 and up about 3.14. And so that'd be less common, but that certainly could happen. And then when you write a point like 3 comma 4, well, that could be xy, 3, 4 like normal, or it could be r theta, where r is 3 and theta is 4 radians, which would be like a little bigger than pi. Pi is 3.14. 4 radians would be a little bigger than that, so somewhere in the third quadrant. So when you write it, there's nothing that indicates that it's polar unless you're told that it's polar. Nothing indicates that it's Cartesian unless you're told that, or if it's clear from the context. So if I say, okay, let's start by converting to Cartesian, and so let's say number 1 is 6 comma 2 pi over 3. So if I want to convert that point to Cartesian, then it's clear from the context that that's a polar point, because we're not going to ask you to convert a Cartesian point to a Cartesian point. We're saying, okay, here's a polar point. Let's convert it to Cartesian. Okay, so there's a couple ways to go about this, but it's helpful if we remember 2 right triangles from geometry or trig. So one of the right triangles that comes up a lot in practice problems is the 30, 60, 90 triangle. So if that's 60 and this is 30, then we can say, okay, this is 1, this is radical 3, and this is 2. And when I say that, I don't mean the sides have to be 1, 2, and radical 3, but I mean the ratios of the sides are 1, 2, and radical 3. And so it's a little bit weird, but like that means if this is 7, then this is 14, and this is 7 radical 3. And I think most of us can figure that out. Is that true? Okay. And so then what's a little weirder is if this is, say, 12, then okay, how would I get the other 2 sides? So if if the hypotenuse is 12, what's the side opposite 30? 6, because you divide by 2, right? And then this is 6 square root of 3 because you multiply that by the square root of 3. Does that make sense to everybody? Okay, and then what's even weirder, or what is actually weird, is that if this is, say, let's say this side is 20, or let's say this side is 12, then to get the other sides, the easiest thing is to go to the side that's 1. And when you do that, you divide 12 divided by the square root of 3. But because of the way algebra works, you rationalize the denominator by making it 12 radical 3 over 3, which is 4 radical 3. And so this side's actually 4 radical 3, which makes this side 8 radical 3. So being able to work with these ratios is something that comes up a lot if we do a lot with polar coordinates. But any questions on what I'm doing to get those? Like if you know one of the sides, we need to be able to get the other ones. Good. Okay, and so we have that special right triangle, 30, 60, 90. The ratios of the sides are 1, 2, and radical 3. We also have a 45, 45, 90 triangle. Man, that does not look like 45, 45, 90 triangle, but now it is. And so we'll say the ratios there are for sure 1, 1, radical 2. And so when you are doing these, you don't technically have to draw a picture, but I think it's easier to. So 2 pi over 3 is somewhere in the second quadrant. This is 2/3 of the way to pi, so it's 2 pi over 3. The reference angle is 1/3 pi, which is pi over 3, and then that is 60 degrees because it's 1/3 of 180 degrees. And that distance is 6. So what we're looking for when we're looking for Cartesian is we're looking for the x and the y coordinates. So the hypotenuse is 6. The side opposite 30 is going to be half of that, so that's 3. The side opposite 60 is square root of 3 times the side that's 1. And so the polar coordinates are -3, 3 radical 3, because their x is negative and y is positive. Does that make sense? Any question? All right. Okay, so let's do one more, or let's do 2 more. Let's say I have 4, 7 pi over 6, and 3 is 5, 3 pi over 4. All right, and so let's do these together. So 7 pi over 6 is 1 1/6 pi, which gets you in this third quadrant. The reference angle is pi over 6 because it's a 1 1/6, so you've passed pi by 1/6 pi, and so this is 30 degrees. The hypotenuse is 4. That means the side opposite 30 is 2, and this is 2 radical 3. In the third quadrant, x and y are both negative, so you get -2 radical 3, -2. Any questions? All right. And so 3 pi over 4 is in the second quadrant because it's 3/4 of the way to pi. The reference angle is then 1/4 pi, which is 45 degrees. The hypotenuse, or the distance to that point, is 5. And so you draw on the triangle. It's 1, 1 radical 2, so you divide by radical 2 to get each of the sides, but that's the same thing as 5 radical 2 over 2. And so then x is negative, y is positive, so it's -5 radical 2 over 2, 5 radical 2 over 2. Everybody clear on that? So it's really trig heavy. It's trig heavy in that, well, I guess not even really trig, but more radian measure. So like knowing how to draw things in radians, that's kind of the key in getting those pictures quickly. And then knowing that it's 30, 60, 90, or 45, 45, 90. I should have labeled this one up here. This is 45, 45, 90. Okay, any questions at all so far? Okay, so this is how you do it when the reference angles are 60, 30, or 45. Or that's one way to do it when the reference angles are those. If you have, let's say, 0, -5, Then 0, -5 is straight down. And so you can label that in a lot of ways. One way to do it would be to say, okay, the angle is 3 pi over 2. And the distance to the point is 5. And so this is one representation of that point. You could also do 5 comma -pi over 2. And then those are probably the two most intuitive, but then there's a lot of different ways that you could end up at that point. Does that make sense? Any questions? Okay, so we should be able to do it if it's 30, 60, or 45 reference angles. We should be able to do it if it lands on an axis. That's technically easier. You just have to kind of think about it. If it's a weird point, so like 3, -4, then you're in the fourth quadrant. So over 3, down 4, around there. And so if you draw the triangle, you can label that as 3 and that as 4. How would we get the third side in that case? We may know it's 5, but in general, how would we figure out the third side? So we could use the Pythagorean theorem. So like x squared plus y squared is equal to r squared. That gets us 3 squared plus 4 squared is equal to r squared. R squared is then 25. So r is either plus or minus 5. And you actually can choose plus or minus 5. It's probably easier to get 5, but you can do that however you want to do it. And then, man, what am I doing? I'm mixing these up. I'm sorry, guys. I will come back and do what I wanted to do on after number 3. This is convert to polar. And I'm going to talk about number 5 in a few minutes. So we're going to come back to that. I'm sorry. I just got mixed up. Anyway, I just got on a different thought process. We'll come back to that. Is everybody following number 4? Okay, and we're going to convert to polar in just a minute. So this does work, but we will come back to it. I want to go and do one more like this where we're converting to Cartesian. Man. All right, so convert to Cartesian. I'm sorry, I messed up the notes. So, okay, the first 3 are ones where I'm giving you the polar coordinates. The reference angles are 30, 45, and 60. Now what I want to do is one where it lands on an axis. So number 4 for converting to Cartesian is going to be the point, let's say 8 comma pi. And so if we have the polar point 8 comma pi, that's over here. Does everybody follow that? Because this is pi and we're 8 units in that direction. If I get the Cartesian coordinates of that point, that's -8 comma 0. So everybody follow that? Again, nothing we did was wrong. It's just something I wanted to cover later. The directions were different. Okay, so those problems are both right. We're not done with 5 yet, but this is what I actually wanted to do. I want to finish doing these first. Okay, so scrolling back up, if you're given polar coordinates, if the reference angles are 30, 45, and 60, you can use these triangles to figure out the Cartesian coordinates. If they land on an axis, you can just look at the picture and determine the Cartesian coordinates. If it's not like that, so if I have, say, 4 comma, let's say 3 pi over 7, let's make it 4 pi over 7. Then I can put 4 pi over 7 in the second quadrant because I know 4/7 is bigger than a half because half of 7 is 3.5. And then obviously 4/7 is smaller than 1. And then I can label this side as 4. And I'm looking for X and Y. It's not a special right triangle, but from the definition of cosine, cosine of 4 pi over 7 would equal x over 4. And that means that then x is equal to 4 cosine of 4 pi over 7. Sine of 4 pi over 7 is y over 4. And that would mean y is equal to 4 sine of 4 pi over 7. So then the polar coordinates to this point are 4 cosine 4 pi over 7, 4 sine 4 pi over 7. And without a calculator, then we don't simplify that further. You don't put a negative sign on the 4 cosine 4 pi over 7 because cosine of 4 pi over 7 itself is negative. And so this is a negative number because it's positive 4 times a value of cosine that's negative. Does that make sense to everybody? Any questions? Okay, so when you're going from polar points to Cartesian, there are 3 main types of problems. So the first type is if the reference angle is 30, 45, or 60. You can use the special right triangles then. The second one is lands on an axis. So if it lands on the X and Y axis, like number 4, and then you just kind of look at the picture. The third is the other type, where it's not a special right triangle. And then you use conversion formulas that X equals R cosine theta and Y equals R sine theta. Those are just modifications of the definition of trig. So cosine is X over R, sine is Y over R, and we just solve those for X and Y. You can use that on all the problems. So if you want to evaluate the trig on those first 2 types, you could do that and you could get the same answers that we got. Okay, any questions on going from polar points to Cartesian points? Okay, now if we're going from Cartesian to polar, it's a little bit less exact because there's more than one way to name the point in polar coordinates. And so let's say I have the point -6, 6 radical 3. So if I'm converting to polar, these are rectangular or Cartesian coordinates. So that's X comma Y. And so we go left 6 and up 6 radical 3. And we kind of do the triangle, but we do the triangle, but we label it backward from what we did before. We think of it backward from what we did before. So now we know the X side is 6 and the Y side is 6 radical 3. And so that's what we know from the problem. Based on that, we can see that the ratio is 1 and radical 3. So then the hypotenuse is double the side that's 1. That makes this 12. So this is what we're figuring out. That means this angle is 60 degrees, which is pi over 3. So the angle we want is 2 pi over 3. And so the polar coordinates for that are 12 comma 2 pi over 3. Does that make sense? Okay. So if I have the point, let's say -7, -7, then we draw that. That's in the 3rd quadrant. So this is 7 and this is 7. From the special right triangles, we can figure out that's 7 radical 2. This is 45 degrees, which is pi over 4. That means the entire rotation is 1 1/4 pi, which is 5 pi over 4. So we get 7 radical 2 comma 5 pi over 4. Does that make sense? Any questions? Okay, now let's go back to the problems that we were talking about up here. Sorry about that. So 0, -5 is not any harder. We'll call this problem 3 now. You still get 5 comma 3 pi over 2. And now the one I want to finish working on is 3 comma negative pi over 4. So when you have, or I'm sorry, 3 comma negative 4. So when you have that, we found r by doing the Pythagorean theorem. And again, r could be positive or -5. But if I want the angle to land there, then I'm going to choose positive 5. And then I'm going to say, okay, the reference angle, alpha is what we usually call that, is the inverse tangent of 4/3. And so we do this in a weird way for a couple of reasons. I want to do one more example in a second, but you choose tangent because 3 and 4 are what's given to you in the problem. You use the reference angle because the reference angle is always between 0 and 90 degrees or always between 0 and pi over 2, which kind of coincides with the domain restriction that inverse tangent or inverse sine or inverse cosine puts on the angle you're talking about. So like inverse tangent, the angle has to come from between negative pi over 2 and pi over 2. So it would never get you this big angle that we want, but it would always get you the reference angle because we treat everything as positive. And so then what we do for theta is we say, okay, in this case, theta is like almost all the way around. And if it were all the way around, it would be 2 pi. But we're missing it by inverse tangent of 4/3. And so then the coordinates are r is 5 and theta is 2 pi minus inverse tangent of 4/3. And without a calculator, that's the best we can do. All right, I want to look at one example like that kind of from scratch, and then I want to talk about the conversion formulas that we can come up with because of that. All right, so again, converting to polar, the fifth problem that I want to do is, let's say I have -2 comma 4. Okay, so -2, 4 is in the second quadrant. So we go to the left 2, up 4. We're going to go ahead and draw, we're going to go ahead and draw a triangle. And we're looking for this angle. And we can use the Pythagorean theorem. We know that's 2, that's 4. We know that x squared plus y squared is equal to r squared because of the Pythagorean theorem. That gets us 2 squared plus 4 squared equals r squared. So r squared is 20. R is then plus or minus the square root of 20, which is plus or minus 2 radical 5. So we're going to choose for r to be 2 square root of 5. The reference angle alpha is here. Alpha is the inverse tangent of 4/2, which is the inverse tangent of 2. Theta is almost all the way to pi, but is missing pi by whatever alpha is. So it's pi minus inverse tangent of 2. If theta were in the third quadrant, it could be pi plus whatever the reference angle is. You want to look at the picture to determine that. So that means the answer here is 2 radical 5 comma pi minus inverse tangent of 2. And that's kind of the best we can do without approximating inverse tangent of 2 on a calculator. Okay, so the conversion formulas we've got we know that x is equal to r cosine theta. We know that y is equal to r sine theta. We know that x squared plus y squared is equal to r squared, which is just the Pythagorean theorem. And then we know that the reference angle alpha is the inverse tangent of the absolute value of y over x. So it's the y divided by x, but ignoring the negative signs. And so those are the formulas we use all the time. The content I want to talk about tomorrow is converting equations. And we use the first two on the left and the first one on the right. So those three equations to convert. But that's all I wanted to talk about today.